I'm Joe Jr. The title of our talk today is Analyzing Microplastic Abundance in Spot Leiostomus xanthurus along Coastal Savannah, Georgia, USA. And the authors for the project is myself, Savannah Geiger, and Dr. Shee. So it's a nice, and watching the other presentation, it's a nice segue in how we transition from microplastics as a whole to shrimp, and now we're looking at fish. So beautifully organized, and I'm really good. So plastics are valued because of ease production and plastic being readily available for human use. However, the high production with the lack of adequate management strategies has led these plastic pollutants to be the most distributed xenobiotic pollutant in all environments. So these environments include the oceanic, terrestrial, and estuarine environments, as you can see highlighted in these infographics here. As both talks mentioned prior, microplastics are defined as small plastic particles less than 5 millimeters in size. The primary sources of microplastics include small microfibers and microfilaments. However, secondary sources of microplastics are larger plastics biodegrading from photolytic, biological, and mechanical processes. These processes are slow, which results in microplastics that have long residence time in the marine, estuarine, and terrestrial environment. As you can see, Dr. Deshpande, he took my infographics, so I'm not going to highlight the same infographic. So the very small size of these plastics make them extremely difficult to be removed via a mechanical and physical filtration. So it is estimated that 4.8 to 127 million metric tons of plastic enter the ocean on an annual level. This could translate to studies like conducted in the Atlantic Ocean that determined that 94% out of 470 water samples had microplastic presence. So inevitably, our oceans could look like a product of something like this, with those lower density polymers accumulating at the surface of pelagic water columns and just accumulating through various other processes that I'll get to later. So distribution. So now let's talk about the vertical distribution of microplastics. So density is a determining factor for where these microplastics will end up in the water column. The less dense plastics will be located in the pelagic water column, while denser plastics will sink to the benthos. And other density altering processes such as biofouling contributes to the overall biofouling is a process of organic material building upon these densities, which increases their sedimentation rate throughout the environment as well. And this infographic here shows you some of the other density altering processes that affect both horizontal and vertical distribution of microplastics. Speaking of horizontally, the spatial distribution of wave energy, such as tides, winds, and other hydrodynamic forces, impact the horizontal distribution of microplastics in the environment. So the presence of microplastics poses ecological risk to biota both in the benthic and pelagic water column. Studies that focus on the effect of microplastic ingestion have recorded a wide range of diverse physiological effects, with some effects leading to evident mortality. So in this infographic you see here just highlights some of the impacts of fish ingestion having on fish systems, which includes acute toxicity of some of the major organs such as the liver, and even toxicity and bioaccumulation in muscle and other key tissues, just to name a few. So microplastics have been reported to alter the predatory responses and foraging behaviors of fish, as they're commonly confused with uncommon prey resources. So in this study, this is one of my favorite infographics as a summary for microplastics ingestion. But this study by Ori et al. Highlighted some of those confusions of microplastics, as these are the common prey resources. Blue copepods highlighted the bottom end part of this infographic, and those blue microfibers at the top hand portion of this graphic. So you can see how this mechanism of confusion, as they're both morphologically speaking, they both look very similar and is virtually indistinguishable from a common prey resource. So microplastics are consumed amongst zooplankton, crustaceans, and higher trophophilic species, which highlights the need for these quantitative assessments looking at microplastic ingestion amongst these varying taxa. So Spot Leiostomus xanthurus are non-selective dentate foragers. They have spatial and temporal distribution. So that means that they're migratory fish that spawn in estuaries during summer months, and juveniles use these estuaries for multiple seasons. And this infographic here gives you a sense of how widely distributed these spots are, as they're one of the most widely distributed cyanidae along the U.S. coastline, the eastern coastline of the U.S. You can see how widely they're distributed from. So the purpose of the present study is to evaluate microplastic abundance in the benthic origin species Spot Leiostomus xanthurus within Wilmington River estuary and Coastal Savannah, Georgia shelf waters. So fish samples were collected on with either a mongoose net trawl or auto trawl. And in this infographic you see here is the ArcGIS map of all 5 of our trawling locations. And this smaller map is our 3 estuarine trawling locations. And in this bigger map, you can see our 2 offshore Wausau Sound trawling locations. And Barry was on that RV Savannah trip, so thank you for helping out there. So samples were dried, measured, and weighed. The measurements were taken from the standard limits. Gill arches and dissective tracts were dissected and placed in a 10% potassium hydroxide solution for protein digestion. After 24 hours, specimens were sieved and then placed at an oven set at 50 degrees Celsius. Then the microplastics were examined underneath a stereo microscope for visual identification of the polymers. So protein digestion was completed according to Falkman et al. 2013 using a 10% potassium hydroxide solution to separate those inorganic contents from those organic contents so we could visually identify those plastics. So as Dr. Deshpande mentioned previously, you need secondary analysis to confirm the chemical composition of the samples in question. So Raman spectroscopy has been a successful tool in deciphering between plastic particles and natural occurring particles. So Raman uses scattering spectra to determine the presence or absence of exciting those outer electrons based on their vibrational frequency. So from exciting those outer electrons, you can get a sense of the chemical composition of the sample in question. So to give you a better example, basically we have our unknown sample here and we hit it with a Raman laser. And based on that measure of excitement, we get an overall spectrum match or a spectrum shift, Raman shift. And then know-it-all software is a library, like Dr. Deshpande mentioned previously, that we compare that to known polymer shifts and get an overall score or a match of how similar those polymer shifts are to our unknown sample. So we did this in collaboration with Dr. Jay Brendis at the University at the University of Georgia Skidaway Institute of Oceanography. And I really do thank you, Dr. Jay Brendis. So now figure 1 shows the frequency of occurrence on the y-axis and all our polymer types that we detect in our spot on the x-axis, which consists of polypropylene, polyethylene, acrylic, polyurethane, and polyvinyl chloride. So we categorize the detected polymers based on their maximum densities reported in the literature review by Roos et al. 2014 displayed in the figure here. So all the highlighted polymers are the ones we detect in our spot, and we use the maximum density ranges of these polymers. As for example, polyvinyl chloride has a large density range. So for example, we just use the 1.58 grams per centimeter cubic for that maximum density. So when we categorize polymers based on their density, we found significance amongst the high density polymers in comparison to the low density polymers. There was a significant greater amount of occurrence of the high density polymers of polyurethane, polyvinyl chloride, and acrylic and estuarine trawls, but there was no significant difference amongst our coastal trawls. And then polyvinyl chloride was almost always the highest occurring polymer type of spot and was statistically greater compared to other polymer types and had the highest maximum density reported by that literature review that I mentioned previously. So the present study gave us a unique opportunity to compare primary microscopic identification or visual identification of microplastics versus secondary analysis of getting a sense of the chemical composition of the sample in question. So there was a mean difference of 6.46 plus or minus 2.16 microplastics versus these 2 sets of analysis. So these results indicate that primary analysis overestimated the amount of microplastic presence, as with visual identification, we're basing on whether or not they're plastic based on the morphological characteristics or physical structure without getting a sense of the chemical composition. So you can see how those means basically translate from primary, what was originally thought to be plastic versus what was actually plastic via Raman spectroscopy. So one of the most striking findings of the study was that we found statistically greater we found significance amongst the different polymer types, and there's a need for secondary analysis via Raman FCR paralytic, as Dr. Deshpande mentioned previously. There was a significant greater amount of high density polymers versus the low density microplastics like spot and estuarine trawls. And then polyvinyl chloride was significantly greater than the other polymer types and the most prevalent polymer types of spot trawling locations. So one of the most striking findings of the study was that we found statistically higher amounts of the higher density polymers such as polyvinyl chloride, which represented the majority of these polymers we detected in spot. However, an interesting dynamic is that the relative density of estuarine water is constantly changing because tides are coming in, influencing the salinity and temperature structure of the physical characteristics of the estuary itself. So when we look at a temperature and salinity profile, this is all ambient seawater. Most of our polymers we detected are relatively less dense than the ambient seawater. So polyurethane, polyethylene, acrylic, and polypropylene are all relatively less dense, all except for PVC. PVC is always consistently greater, had a higher density than ambient seawater. So we need to consider the foraging behaviors when assessing microplastic ingestion. Again, Spot are benthic deposit feeders and had the highest abundance of the higher density polymers, such as polyvinyl chloride. So this makes sense because Spot are benthic deposit feeders and they're sifting through the sand to get their foraging needs and get their nutritional value. So they come into contact with those denser polymers and those denser particles at question. And it's cool that we saw that reflected in their digestive tracts and their gill arches. So when we compare the results to a recently studied literature review of microplastic in fish, there's a large number of striking similarities. So first, plastic ingestion is heterogeneous amongst taxa, and there is differences that you need to decipher in order to determine the microplastic ingestion. So estuarine fish consume more plastics. So that supports our statistical significance that we found in our coastal spot versus our offshore spot that we collected in our sample sites. And then active predators and benthic foragers ingest more plastics. And again, Spot are benthic foragers, and they ingest more of those higher density polymers such as polyvinyl chloride. And then finally, studies that chemically digest the gastrointestinal tract, filtered solvent material, and use microscopic identification reported a higher amount of microplastic concentration. So again, this is kind of like a check mark to say that our methodologies were appropriate for assessing microplastic ingestion within these spots. So now the next steps of publication. So first we need to finish conducting Raman analysis. So finish conducting secondary analysis on samples already in storage. We are currently comparing amongst different foraging ecologies, and I just didn't finish it within time and within reason. So we need to determine what are those trends amongst those different foraging ecologies. So the common trends amongst species we need to assess for is there a similar density effect in other fish species? And what are the trends in polymer types on microplastics? And can we see that density stratification amongst different foraging ecologies like filter feeders, benthic deposit feeders, active predators, and so on and so on. And then finally, the end all be all goal is like the golden globe, I guess, of all of this, is can we achieve a microplastic model? So using the data as a basis, can we predict microplastic abundance amongst fish with varying foraging ecologies and use it as a vulnerability value of microplastic ingestion, using the data as a basis and modeling based on those predictive values. So I'd like to give a huge thank you to Dr. Jay Brandis at Skidways Institute of Oceanography for offering his mentorship and guidance throughout the duration of this project. I also want to give a huge thank you to all the micropilots, that's what we call ourselves in the lab, and all the students and graduate students that contribute to this research. And thank you, Savannah State University, the entire Department of Marine and Environmental Science. And thank you, NOAA LMRCSC, for funding me throughout my college career. And thank you guys for having me. Yes, go ahead.
That's a great talk. Thank you. Do you think it might be possible one day, maybe it is now, but if you just looked at the muscle in the fish, that you could get an exposure and figure out that the fish has been exposed to microplastics?
Right, that's a great question. So one of the things I think about when thinking about those physiological responses is like we a person mentioned previously, just a retention time. So these microplastics, the polymer itself, the root definition is just many. So they're composed of many different chemical compositions in question. But however, if you have different phthalates or different PCBs, you'll have those muscle responses to those organic compounds. So it all depends on what the chemical composition of the sample. And yes, that is definitely a goal we want to achieve in the near future. And I definitely like the direction to go. Yeah.
Nice presentation.
Yeah, thank you.
You show that 46% of all Spot had microplastic in key tissues. What tissues are you referring to?
So the two tissues that I looked at was the gill arches and digestive tracts. So we looked at the gill arches because these fish have heavy interaction with the benthos and their sand teeth. they're sand sifters. So they actively go through the sand and then sift through different particles. And then another thing to mention is just a lot of these plastics are biofouls. So the fish, they feel that organic material throughout their gill tissues. And so they might ingest it thinking it's actually like microinvertebrate, for example, because it doesn't have like the structure of a plastic or unknown sample. So we looked at those two key tissues, and that 46% of all those on spot that had confirmed polymers in either gill arches or digestive.
So we have the plastics on the gills or inside the gill, gills.
Right, stuck in the gill arches or inside the digestive. Yeah, go ahead.
This was a great presentation.
Thank you.
I have two questions.
Yes.
First being, how did you find out about the potassium hydroxide usage to separate them? Did you just find it in your like literature review before you started, or like did you have to find that out some other way?
So yes, that's a great question, and Julian could attest to this too as well. But like, I'm so glad I'm working with fish and don't have to deal with an exoskeleton, because digesting that exoskeleton, we had tales of other students having a long, prolonged protein digestion session. So basically with the KOH, it was accepted in the literature review. And so that 10% was like that magic number that everybody alluded to. And that literature review that I showed previously, a lot of studies use that 10%. And then of course, the size of the fish or whatever fish you're looking at impacts how long that takes, or whatever digestive or whatever dissecting tissues you're looking at. So you just have to time it accordingly. Yeah.
And did you also find other publications that talked about, for example, you said if you had other species studied, you could see how each species, for example, pelagic species would have the less dense particles accumulated. Have you seen other publications on that?
Right. So that's one of the interesting dynamics. A lot of the publications I came across was looking at single species. So like I want to get like more of a holistic view and just looking at various foraging ecology. So like I wanted to include this slide, but I didn't have enough time to accurately explain it. But another fish species we're looking at is bay anchovies and flatfish, southern flatfish. So bay anchovies, those are pelagic filter feeders, and those flatfish are demersal feeders, but they have a little bit different foraging ecology from spot. But some interesting things we're seeing from our bay anchovies, we're seeing a lot of those less dense polymers. We're seeing a lot more color. So those are those plastics that are less dense and have some of those gut dyes associated with it. So those are some of the preliminary results we're seeing right now.
Did you find a difference in the number of microplastics found in the gills and the microplastics?
Right. So yes, we did test for that, but we didn't see a significant difference. So we ran the Dunn's test. We ran the Gartlett's test to test for normality. Then we used a Dunn's test to test for standard length. We did standard length, but we also did against those key tissues, and there wasn't a significant difference. So it was a lot of variability, and again, retention time impacted that. So like basically, whenever we collected the fish, they're a product of whatever they were exposed to in between that time. So like it's that's probably the reason why we didn't see that significant difference amongst those. But yes, great question.
You mentioned the modeling at the end. I was wondering like what you're thinking of, like are you like trophic transfer or like just for some modeling, like the plastics in the ocean?
Yes, those are two areas I was thinking about. And then overall, just a quantitative assessment and just seeing if we could make those assumptions based on their foraging ecologies. And so like I don't have a top predator like a shark on here, but if I would definitely include it in the end-all be-all microplastic model. And then the trophic transfer dynamic, again, is just a product of when did they actually consume that fish or that shrimp or whatever they consume, ingested microplastics, and then got it in your gut, gill arches, and so on and so on.
Thank you.
Last question.
I had many, but down to a few. So have you considered the change in density that microplastics witness from the environment, whether by weathering or even fouling, because as we are observing, microplastics aren't staying within the water column, that they are settling onto the seafloor. And have you considered that, and how does that relate to the research that you're doing now?
Right, that is a great question. And a lot of times these plastics were hypothesized are secondary, so they're not exactly pristine from the manufacturer they were originated from. So like A lot of these times they're biodegraded, and so that's what makes the ramen spectrum matches kind of different. So that's why that example I showed previously had 97%. There was some that were like that was some that were like 75%, there was some that 85%. So that could be a product of degradation and affecting the sample in question. So like anytime these fish or whatever species ingested, there's some sort of chemical digestion, digestive acids associated with that, or just being in the environment, biobalance, density altering processes, abrasion, absorption of chemicals, all those factors that play a role in it. So, yeah, great question. I would love to talk about.
Great response. Thank you.